This is AS Maths 2021, Paper 1, Question 12. This is a 9-mark question involving trigonometry. We can see if we glance through cos squared theta, sine theta, and then further down the page, we've got tan x, sine x, cos x. So we've got all three trig functions appearing within the context of solving trigonometric equations. We'll start out at the beginning. We should recognize this format of equation. We've got 5 cos squared theta equals 6 sine theta. And although in its current form it doesn't look particularly easy to solve, that doesn't necessarily mean that we haven't got any tools at our disposal. Remember, with Year 12 A-level maths, there are 2 important trigonometric identities in addition to right-angled trigonometry, SOHCAHTOA, and sine rule, cosine rule, and the sine area formula. We also have these 2 very important formulae up our sleeves. Tan theta is equal to sine theta over cos theta. That allows you to convert tan into a combination of sines and coses. And the Pythagorean identity, as it's sometimes called, sine squared theta add cos squared theta is equal to 1. In fact, both of these can be thought of as identities rather than simply equations. We can put a triple equals sign because they are always true. Regardless of the value of theta, regardless of the angle we choose, tan theta is always going to be sine of theta over cos of theta, and sine squared and cos squared theta will always add together to give 1. What that means is, anytime we see sine squared theta or cos squared theta, we can replace it with something involving the other one. So for instance, sine squared theta can be thought of as 1 minus cos squared theta, or alternatively, cos squared theta can be thought of as 1 minus sine squared theta. And that's really important because in this context, we have a problem that would be more readily solved if we could write cos squared theta in terms of sine squared theta. So that's exactly what I'm going to do. I'm going to take that cos squared theta and I'm going to swap it out for 1 minus sine squared theta. The reason that's a good idea is that now what you're looking at is still a trigonometric equation. It still has trig functions appearing squared, which may make things seem more complicated. But the fundamental difference between this equation and the one you were given at the beginning of the question is that this one involves only one trigonometric function. It involves sine theta and powers of sine theta, which means that under the hood, this is a quadratic. We call it a quadratic in sine theta because we can write it, if I shunt everything onto the right-hand side, we have 5 sine squared theta plus 6 sine theta minus 5, and then I'll stick my 0 on the other side here. This should remind us of trigonometry, of quadratic equations, because it's got a constant, it's got a thing, and it's got the thing squared. And in fact, if it makes it easier for you, you can even make a little substitution, that s equal sine theta, for instance. And then you'd be looking at 5s squared and 6s minus 5 equals 0. If you can avoid doing that, I think I would recommend not bothering with that, mostly because it's easy to get confused if you're using awkward letters like s, but also because it's easy and very tempting to think you're finished when you found the value of s, whereas in fact, you won't have solved part I of this problem until you've found solutions for theta. So although you can think of it in your head perhaps as 5s squared add 6s minus 5, remember that what you're dealing with is actually sine theta. And after you've found any possible solutions for sine theta, you still need to go ahead and find the corresponding solutions for theta itself. Now, the easiest way to solve any quadratic, including a disguised quadratic, is going to be with the calculator. So go to menu option A, choose polynomial, degree 2, and then we'll put in 5, 6, and minus 5 for our A, B, and C values. When you press equals, it gives us our solutions. Now, this looks a bit messy, but if you press SD, you can see that it is, in fact, a decimal value that is somewhere between -1 and 1, which is encouraging. And if we press equals one more time, we get another value. This one is not between -1 and 1. That's fine. It's not a big problem for us, but it's worth noting that one of our solutions, -3 plus root 34 over 5, is the kind of value we might expect sine theta to take, whereas the other one, -3 minus root 34 over 5, is not. So when we solve, we don't need to write anything more sophisticated than just sine theta equals, and then the solution that the calculator gave us. So -3 root 35, I forgot what it said, -3 plus root 34 all over 5. And then the second possible solution was the same sort of thing, but with a minus in there. Now, this value, we've already checked, did this with SD. We know that this one is the kind of value that we should safely be able to do inverse sine of. So what you can do is go to menu option menu option 1, sorry, we're back to ordinary calculator mode. And then we can just do inverse sine of our answer. And we've got a problem. I'm not quite sure where that problem came from. Let's check what the answer is. The answer somehow has not been saved. That can happen occasionally if you're in a different mode. So we're going to go back to quadratic solver mode, and we're going to go into here, and I'll show you how to get around that. 5, 6, minus 5. Now that looks like an answer on the screen, but in fact that is just something from within the quadratic solving mode. It should be possible to press store, and then you'll see this tiny little thing comes up that's got an arrow pointing to an X. You can choose X if you like. That might be the simplest. Stored to X. Or you can choose A, B, C, D, E, F, X, Y, or M. Any of these letters that have got, these keys that have got little pink letters over the top of them. Now when you go to calculator mode 1, you can either press Shift and then the STO button to see any values you've stored, including X. You see that 0.566 that we had there. Or, which is probably simplest, you can just type X, and there it is. What we need is inverse sine of X, and that gives us a sensible value for theta. Unfortunately, my calculator is in the wrong mode, so although this looks like a sensible value to me, I'm happy to understand it in radians. You want to double check that your calculator is in the correct angle mode, so you press Shift, you hit the menu setup button, and you can choose the angle unit, option 2, degree, radian, or gradian. Nobody at A-level uses gradians. I think they're used by surveyors potentially. Radians you'll come to in due course, but degrees for now. Now if we try inverse sine of X one more time, it should give us an answer in degrees, one that we can make sense of more readily. 34.5 degrees. Now, I'm looking at the question at this point to figure out exactly what level of detail I should include. It says give your answers to one decimal place. Ideally, what that means is we should do our working out to a greater number of decimal places. 34.48 might be a better number to write down here. So we'll keep our answers to at least 2 decimal places so that our final values can be written to 1 decimal place, and we won't have lost any precision by perhaps subtracting from some number and rounding incorrectly at the end. Now, that's the first solution. That's the one the calculator gives us. But remember that when we're solving a trigonometric equation, we need to consider all the possible solutions. This doesn't have to be a particularly fancy process. What I would recommend is you draw yourself a rough sketch graph. So it can be fairly rough and ready, but what it does need to indicate is the behavior of the function you're looking at. This is a sine wave, and I know, for instance, that its peak happens at 90, and it's going to have a 0 at 180, it has a trough at 270, and gets back to its same starting value that it had at 0, all the way up at 360. Now, I'm trying to solve an equation that had sine theta equals 0.5 something. So I'm imagining a line across here where the y coordinate there is like 0.5-ish. And I don't really care about that value. What I care about is the symmetries of the graph and how they're going to help me to find an additional solution. One of these solutions I've already got. I know that there is a value here. I found it. It was 30 something degrees. So what I need is to link it to the value over here. So that's what I'm going to do. And I'm going to use the fact here on my graph that the angle is going to be just as far in from 180 as my original angle was in from 0. We've got symmetry about the 90-degree mark. Another way of saying that is that the two angles will have an average of 90, or they will have a sum of 180, which means I can subtract from 180 and get another valid angle. So that's what I'm going to do here. Use my rough and ready sketch graph to get me an additional solution. 180 minus 34.48, which the calculator can help me with. I've still got that on the screen. So 180 minus answer 145.52 looks like. So we got sine theta, and that gave us one angle directly from the calculator, inverse sine of this complicated number. And then we got a second solution using the symmetries of the graph. But is that all? Now, if we look at the original question one more time, solve for naught is less than theta is less than or equal to 450 degrees. Now, I've gone with the default version of a sketch of the first 360, and arguably you don't need a bigger sketch than that. You shouldn't ever need to sketch some weird combination of sine functions to solve an equation like this. You shouldn't need to sketch it going backwards and forwards a long way. We can use the first 360 to take advantage of the symmetries of the graph. And then to go beyond that, all you have to do is add multiples of 360 to your angles until you run out of angles that you need. So we can also have 360 plus 34.48, which is going to be 394.48 degrees. And we could try 360 at 145.52, but you might see already that's going to give us 400, 550 something, and we don't need to go that far. 450 is the maximum we need to get to. So we don't need this last one. We can dispense with that particular one. It's going to be too far up for us to care about. So let's leave that one behind, and we're content with this third solution that we've come up with here. But all of that working out, that all corresponds to sine theta equals minus 3 plus root 34 over 5. So far, all we've done is investigated one of the two possible solution branches, if you like. Our quadratic solves to give two solutions. One of them corresponds to these angles. In other words, if theta is equal to this angle or this angle or this angle, then sine theta will be equal to this 0.5 something. And if sine theta is equal to that, then 5 lots of sine squared theta add 6 lots of sine theta minus 5 will be equal to 0. But it's a quadratic, so there's probably another value that sine theta could take that would cause this quadratic to be equal to 0. And that's what this second solution branch is going to do for us, potentially. We need to look into this one to determine whether or not there are other values of theta that would give a different value for sine theta, which would still solve the original quadratic. However, as we mentioned when we first looked at this, minus 3 minus root 34 is not within the range you would expect to see for a sine function. Minus 3 minus root 34 all over 5. If we press the SD button, minus 1.766 something. So all I need to write here is something like this is less than minus 1. Therefore, no solutions for theta. If sine theta could take this value, then we'd be able to solve it and find solutions. But it's effectively, it's like saying, let's see when my sine wave crosses a line which is too high. it never crosses. So there are no values of theta for which sine theta will be -3 minus root 34 all over 5. And that is the end of part I. 5 marks worth in that. There will be a mark in that mark scheme for recognizing and applying this identity, sine squared theta add cos squared theta equals 1. So if you attempt to replace cos squared theta with 1 minus sine squared theta, even if you make some mistakes along the way, there will be a mark for that. Then rearranging and attempting to solve the quadratic, there'll be more marks for that. Using this to find some solutions, there'll be an answer mark for probably one valid solution, and then there'll be more answer marks if you get additional valid solutions. And then there'll be some method mark, presumably for showing that this yields no solutions. So it's worth noting that just spotting that it doesn't have solutions and ignoring it is not necessarily enough. You want to state how you know that it does not give you any additional solutions. Before we move on to the next part, note that the next bit doesn't relate directly to the first part, so we don't have any obvious way of verifying our answers to this first part unless we do it for ourselves. So that's what I'm going to show you briefly on here for the next bit. I am in menu option 9, table mode. Table mode lets you enter a function, 2 functions if you need to. That can be quite helpful for verifying solutions to equations. I can take, for instance, the left-hand side of the original equation. I tried to use the one that was given in the question rather than one that I've constructed myself in case I've made an error in constructing an equation. So I go right back to the root 5 lots of cos x squared, and that is my f of x. This is going to give me a table of values for the left-hand side of the equation. And then on the right-hand side, after I press equals, I can put in g of x. I'll do 6 lots of sine x and press equals again. My table range will let me do various things. I can probably go up from 0 to, well, we might go up to 450. But I probably don't want to go up in steps of 1 because the calculator will complain. Range error. So I'll go back and I can still use these, but I need to modify my range. So I'll make the step 30 degrees and see if it's happier with that. Here we go. And although it's fairly limiting what you can put in for the range, note that you've got a fair few spaces in here that you can fill, and you can put numbers in for yourself. Now we can see here the left-hand side and the right-hand side of the equations in general do not match. But that's okay, because what we're looking for is not hunting for solutions. We've got potential solutions already here. We've got 34.48. So if we type it in, we can check 3.3975. That's what the left-hand side evaluates to at that angle. And 3.3967, that's what the right-hand side evaluates to. Don't be too surprised that they're slightly different. That's because the angle we've put in was only accurate to 2 decimal places anyway. So the solutions, the left and right-hand sides will not be identical to each other because our angle is not identical to the correct angle. If, however, you wanted to put in something a little more precise, you could put inverse sine of -3 plus root 34 all over 5. And that would mean the calculator is now using the most precise version of that number that it can. And now if you look, 3.397142274, and the next one is identical. There's no difference on the calculator screen at least. So if you want additional verification, you can get it from there. But the quickest way is just to type in your numbers, 145.52. They match for that one as well. They both give 3.3975. Not only do the left and right hand sides match, but they match with the same value because both of those angles should give the same value for sine of theta. And remember our final one that we worked out, 394.48. We can test that in the same way. I want to point out one thing here. If you hadn't noticed that the solution ranges from 0 to 450, you would have missed that final solution. And our verification method, although it's great for telling you that these two are valid solutions, it's not going to flag up the fact that you've missed an alternative valid solution. And equally, if there were other solutions from the other factor from your quadratic, this method wouldn't tell you that you've missed any. So watch out for that. The other thing to mention is the wording at the top here. In this question, you should show all stages of your working. Solutions relying entirely on calculator technology are not acceptable. What we've done here that relied on calculator technology was solving a quadratic. And that's never going to warrant you more than 1 mark in an A-level maths paper. And you are perfectly entitled to use the calculator to solve the quadratic for you. As far as they're concerned, you might have looked at it, used the quadratic formula, and jumped straight to this point. Whether you use the quadratic formula or use the calculator mode, it doesn't make a difference. You've correctly solved it. So you don't need to show that you've done this factorized by hand or anything like that. It wouldn't be easy to factorize by hand anyway. But let's say you worried that you were supposed to complete the square. That's not what it's suggesting. What it is suggesting is if you decided to brute force the answer by starting at 1 degree, 2 degrees, 3 degrees, 4, 5, and you started hunting for solutions like this, or at 20 degrees, we've got 4 on one side and 2 on the other side. At 30 degrees, they're closer. At 40 degrees, they've switched sides, so maybe there's an answer somewhere between 40 and 30. You could home in on the correct answer like this, probably relatively quickly. 35 degrees, the left-hand side is lower. 34 degrees, the right-hand side is lower. So we're probably somewhere between 34 and 35. With this approach, you could pretty much guarantee yourself getting the 34.5 degrees that they're wanting, but that wouldn't indicate that you understand how to solve the equation. So that's the method that they're telling you can't use. It does not mean that you can't use the calculator to verify answers that you've independently found for yourself. The final thing to mention is that it tells you to give your answers to one decimal place. Depending on the mark scheme, they'll sometimes be lenient if your answers round to the correct value to one decimal place. But when we get to the final line for our solutions, we want to make sure we've not only solved the problem we were given, but we give our answers in the required form. So at the end of this part, to make sure we've done it and we've done it properly, all solutions in the range will be theta equals 34.5 degrees, 145.5 degrees, and 394.5 degrees to one decimal place. Now, that was part I. Let's have a look now at part II. This is 4 marks worth, and although it looks longer, it's not necessarily as long. A student's attempt to solve the question, solve for minus 90 degrees to 90 degrees, the equation 3 tan x minus 5 sin x equals 0, is set out below. Now, I like these questions. I like the fact that if you're revising by using a question like this, it helps you to alert your brain to the kind of common mistakes that you might make if you're solving a problem like this in an exam. But also, if you're a little rusty on what you should do, it at least gives you some clues. So you can read through it and see that actually, even if this student has made some mistakes, it says 2 errors or omissions. So they've done a fairly shoddy job. If you think about errors per line, it's a fairly high proportion. But they have still attempted to do reasonably sensible things throughout. And the errors they've made are perfectly understandable errors once you look into it. And they're errors that, although they might not be obvious for you to spot, they're really important ones and useful to identify. So let's get into it. The first thing they've done, if you look carefully, the only thing that's changed is tan x has changed into sin x over cos x. Not only is this not an error, this is the optimal thing to do with an equation like this. Remember, we mentioned there are a couple of identities that you get in AS maths or year 12 A-level maths, and one of them is tan theta equals sin theta over cos theta. If you remember that one, anytime you're dealing with an equation that involves tan theta or tan x, you know that you can convert it into something involving sine and cos. That's useful because it will allow us eventually to reduce things down and hopefully turn our equation into simpler equations involving just a single trig function. So they've converted to sine over cos, and then the next line. In the next line, 3 sin x over cos x becomes 3 sin x. So cos x has disappeared from the bottom of the fraction. But they've not just got rid of it or forgotten it, because you can see in the other term on the left-hand side, minus 5 sin x has become minus 5 sin x cos x. In other words, they've multiplied the entire left-hand side by cos x. This is also a sensible thing to do, because previously we had an awkward fraction. Now we have something that doesn't involve fractions. Maybe you would have added 5 sine x to both sides before multiplying through, but you'd end up with an equivalent expression. So far, so good. On the right-hand side, notice we've got a 0, so multiplying by cos x will not affect the value of the right-hand side. 0 times cos x is still 0. So we're running out of places where the mistake might have taken place. If we look at the next line, work out what the student's done. 3 sine x becomes 3, minus 5 sine x cos x becomes minus 5 cos x, and we've got zeros on the right-hand side still. So it looks like they're divided through by sine x. And then the line after that, they've rearranged. Looks like they've rearranged correctly. If you add 5 cos x to both sides and then divide by 5, you get cos x equals 3/5. And then you could do a quick verification on your calculator to see if what they've got really is what they should have got for that final step. Inverse cos of 3/5 really does give 53.1 degrees. So what's gone wrong? Well, you might be thinking of doing a similar thing to what we did at the beginning to verify your solution. You can verify more directly by doing 3 lots of tan 53.1 minus 5 lots of sine 53.1 and see if we get an answer close to 0. Minus 2 times 10 to the minus 3 is close to 0. It's not going to be exactly 0 because I'm using a rounded version of the angle, but it's close enough that I'm convinced that this is a valid solution. So what's the problem? If it's a valid solution, why is it an error? Well, I think the key phrase in here is errors or omissions. Not necessarily something that's a thing that was done wrong, but a thing that was done wrong by dint of it being left out. Something you've done wrong by not having done something. You didn't deliberately set out to do something wrong, you just forgot to do the dishes, or you didn't put the toilet seat down. This is an error by omission that's going on here. Something they've missed out, or something they might have made a mistake with by not doing enough of. And one clue actually comes from reading this bit, or from thinking back to what you did here. We were looking for solutions to this, and we found loads of them. In fact, we know there will be many of them because it says giving your answers, plural. And down here it talks about the first 4 positive solutions. So there must be a whole bunch of solutions even to this simple equation. Why is it that we only got one solution here? The first thing we'd be thinking is, well, maybe that's the only solution there is between minus 90 and 90. It's quite a narrow range after all. The cos graph between minus 90 and 90 is symmetrical on both sides. So if cos of x equals 3/5, that doesn't necessarily mean that x has to be 53.1. In fact, you can check for yourself that cos of minus 53.1 also gives something that looks remarkably like 3/5, 0.600 something, with a rounded value. So clearly he's missed out a valid solution, and that's one of the errors. There's something else a little more subtle. So I want to do something that I'll occasionally do with a question like this. If I'm stuck, I'll try working it through for myself. And as I go through and find the bits that went wrong, maybe I will make or almost make the same mistake. So I'll start at the line that we were reasonably happy with. We replaced tan with sine over cos. We then multiplied through by cos. We've got 3 sine x minus 5 sine x cos x equals 0. Now, on the very next line, our student has lost sine x from here and from here. When are you not allowed to divide by something? Seems like a bit of a strange question until you know the answer. There is one particular number that you would never divide by because it doesn't make any sense. You can't share between 0 people. You cannot divide by 0. And it's obvious if it's the number 0. It's less obvious if that number is hiding within the guise of sine x. It is perfectly possible for sine x itself to be 0. In fact, sine x is 0 from time to time. It's 0 when x is 0, and again when x is 90, and so on. So a better solution than dividing by sine x and effectively losing potential solutions, because if you're dividing by it, it's almost like you're saying, well, it can't be 0 because otherwise I wouldn't be allowed to divide by it. So instead of dividing, we're still going to remove it because we want to get this 3 minus 5 cos x. That's not an invalid solution stream, but in addition to that one, we're also going to have sine x. So we are going to take out sine x as a common factor instead of dividing by it. Basically, we don't want to ignore the possibility of a solution arising from sine x equals 0. And in fact, generally speaking, if you ever have an opportunity to divide through by sine x, it's because sine x is a factor. And if sine x is a factor, it is going to give you solutions. We find our solutions by either sine x being equal to 0 or 3 minus 5 cos x being equal to 0. So you can see we've got a whole other solution stream. If sine x is 0, we can use our calculator to get inverse sine of 0, which is just 0. We've also got additional solutions because remember from our sine wave, we don't need to redraw it because we've got one here. Where do we get zeros? We get one at 0, we get one at 180. If we went backwards, we'd have one at minus 180. If we went forwards, we get one at 360. But if we check our solution range here, we have a much more restrictive range. And sine only has one solution within the minus 90 to 90 range. So although we do find one additional solution, it's only one additional solution. We don't have a whole load of them from this one. So we found one of our errors. You divided by sine x instead of taking it out as a common factor. What about the other error? 3 minus 5 cos x equals 0. I'm happy that you did this bit right. 3/5. We get x equals 53.1 degrees by doing inverse cos, just like the student did. But we also get this additional solution. We get minus 53.1 degrees. And that just comes from the symmetry of the graph. That is the second error that the student made. So if we go back and double check the two errors made, giving a brief explanation of each, we'd be looking for something like the student divided by sine x on line 3 instead of extracting it as a common factor, or instead of recognizing that sine x equals 0 also gives a solution. And then the student only gave one angle as a solution for cos x equals 3/5 instead of taking into account the additional solutions within the range, e.g. minus 53.1. The final thing we can do here is check, and we can even do this without the calculator, that the additional solution we did find really works. 3 times tan of 0 is 0, tan 0 is 0, minus 5 times sine of 0, that's also 0, and 0 take away 0 is 0. So the additional solution we found really is a valid solution. Now we get on to the final part of this question. The first 4 positive solutions in order of size of the equation cos 5 alpha plus 40 equals 3/5 are alpha 1, alpha 2, alpha 3, and alpha 4. Find, to the nearest degree, the value of alpha 4. Now this is worded in a somewhat different way to the previous questions. They've not given us a solution range. What they've given us instead is, can you find the first few positive solutions? But also, we've been helped out a little bit because cos of something equals 3/5 is something we already have some knowledge of. We've just solved it, at least for minus 90 to 90. So is that going to help us? Well, here we had cos x equals 3/5. Here we've got cos of something else equals 3/5. Cos of 5 alpha plus 40 degrees. However, you don't need to worry about the horizontal translation and horizontal stretch that this corresponds to, not for this question. All you need to worry about is all of the valid solutions for 5 alpha plus 40. And when you've got all the valid solutions for 5 alpha plus 40, then you can figure out the valid solutions for alpha by subtracting 40 and then dividing by 5. So really, we can think of 5 alpha plus 40 as being equivalent to x. If 5 alpha plus 40 is x, then solutions for 5 alpha plus 40 must just be the same solutions we found for x. 53.1 degrees minus 53.1 degrees. We can look for more. Remember, these two came from symmetry. Cos is an even function, so if it has alpha as its solution, it also has minus alpha as its solution. But once we've got a couple of values using symmetry, we can just start using the period of the graph. So you can get your first solution, which was 53.1. You can just add 360 to it. That gives us another one, 413.1. And we can also do the same thing with minus 53.1. We can just take minus 53.1 and add 360 to it, and that gives us an additional solution, 306.9. Now, we've got 4 solutions here, but they're not all positive. And in fact, we've got this plus 40 here, so depending on how large this solution had ended up being, even that one might not have corresponded to a positive value for alpha. In this case, it should, because 53 take 40 is still going to be 13. 13 and a bit divided by 5 is still going to be positive. But this one is not going to help as much. That one is going to give us a negative value even after we subtract 40 and divide by 5. So we're going to need to go a little bit further. They're looking for the first 4 positive solutions. We've got one positive solution for 5 alpha plus 40, which should correspond to a valid value for alpha. We've got a couple more here. We need to look a little further afield. So we just keep adding 360. The next one we're going to get is from 306.9 and 360. So that gives us 666.9. And you'll notice I didn't have to worry about the symmetries and the period of this weirdly transformed curve. To get all of these, I'm using the standard symmetries of the ordinary cosine wave. And once I've done that, then I perform the conversions. So I'll take my 53.1, I'll take away 40, and then divide by 5. And my first solution, therefore, for alpha will be 2.62 degrees. The next solution I can find, it says find to the nearest degree the value of alpha 4. This is why checking on the question every now and then before you do too much work is a good idea. They've not asked us for all 4 solutions. They've said, here's the first 4. What is the 4th one? So now I've found these, I know where the 4th one's going to come from. It's going to come from this one. So I don't need all the possible values of alpha. I need alpha 4. And it's going to be 666.9 minus 40 divided by 5. It's a good job I'm working to 1 decimal place here, at least, because I need to the nearest degree the value of alpha 4. And if I lose some precision along the way, I'm not going to lose so much that my answer is off by that much. Take away 40, divide by 5, and we have 125.38. Finally, we write our answer to the nearest degree, just as the question has asked us. You'll notice this question was only 2 marks. All you're really needing to do is recognize that there's a bunch of equivalent solutions to cos of something equals 3/5, find one that's the 4th positive one we're going to find, and then convert it back. You can check, if you like, that 125 degrees, if you multiply it by 5 and add 40, gives you 665. Cos of 665, not far off 3/5. It's off by a little bit here, 0.57 instead of 0.6, but that's because we're only giving our answer correct to the nearest degree. If here we tried cos of 666, is 5, 8, and what are we doing? 1, 2, 5, 1, 2, 6 times 5 and 40 is going to be somewhat bigger. That comes out 0.64. So either side of my 125.38, you can see we're getting answers either side of 3/5. But the main thing here that you're not necessarily going to get by checking on a calculator is that this is the fourth positive solution. What I would highly recommend is a quick sketch graph, just to make sure you're confident with where you're going. So you draw yourself a cosine wave, and in this case, I'd be tempted to keep it going a bit because we're looking for the first 4 positive solutions, and its inverse cos equals 3/5. So we draw a line along and you try to figure out where those solutions might be. The first one, the second one, the third one, and the fourth one. Clearly, one of the solutions is going to come in here just before the 90-degree mark, and then another one will come in here just after the 270-degree mark. There'll be one up here after 360 and one up here after 450. And that's consistent with what we saw. I wouldn't recommend trying to sketch a cos of 5 alpha minus 40 or whatever the graph was, or 5 alpha plus 40, because it's going to take you too long to think through the order of those transformations. The order matters there because you're translating and stretching both in the x direction. So things can get rather complicated. But what you can do for this 2 marker, just to make sure you're on the right lines, is convince yourself that these numbers are sensible values for your first 4 positive solutions. And that's it. That is your 9-mark trig question.